Hello everyone, this video is focused on the laws of indices and their applications. And first of all, I would like to discuss very briefly about this. Let's say we have a times x to the power b. As you might already know, this a and b are the unknown constants and this x is the unknown variable. A happens to be multiplied with this x to the power b. So a is called as a is the coefficient of x power b, and this b is the exponent, normally called as power of x. So with this basic knowledge, let's move on to the rules of exponents. I'm going to list all the rules of indices and I'll try to be clear about each of them. So the first rule is when same bases are multiplied, let's say a power m times a power n, then same bases are multiplied, then you add the powers. Rule number 2 is you can guess from here, if it is multiplication, you add the powers. So if it is same bases divided, you will subtract the powers. Number 3 is a power n is 1 over a to the power negative n. That is to say, when you are shifting any base across the numerator and denominator of the same fraction, the sign of its power is reversed. Now that also means you can see this insight here. If we could write as, if you write it as a power m over a power n. Now if I bring this a power n up in the numerator, so n is subtracted because the sign of n is changed. But on the other hand, if I bring a power m down in the numerator, it will have a negative power. It will have a negative power. So a power n as it is and power m is subtracted there. So you can relate from rule number 3 how does this happen. Then rule number 4 is power of power. If you have a power n and you're taking power m of that as well, so you simply multiply the two powers. If there is power 0 for any number, that's equal to 1. I'm not going into proof of these, so I'm just listing quickly whatever the rules we have. Okay, next comes if we have different bases but the same power. Let's say a power m times b power m. So the powers are same, but the bases we are multiplying are different. This is not like rule number 1. They had different powers but the bases were same, so we were able to add or subtract their powers. But this time it's different bases with the same power. What you can do is you can write that as whole power. This power m is the whole power of this product of a and b. It must be noted that you should be able to very easily identify in both directions. If you're given the whole power of a product, then this whole power is distributed to each of the bases. And similarly, if you have different bases with the same power, they can be written into one whole power. Let's move on to the next rule, that is the 7th rule here. So if it is multiplication of different bases with the same power, we collect the whole power. Similarly, if we have a power m divided by b power n, bases are different but the exponents are same, we can write as whole power of this fraction. And in the other way around is if we have the whole power of the fraction, then this power is given to the numerator and to the denominator. Rule number 8. Rule number 8 is actually not a listed one, but I would like to include in my video here, is that looking from this, many students tend to make the same mistake and say that if it is a plus b or a minus b to the whole power m, they could distribute this whole power. This whole power concept is not applicable for addition and subtraction. It's only for multiplication or division. So please make sure that a plus b whole to the whole power m is not the same as a power m plus b power n or a plus a power m minus b power n. Let's take an example for that. Let's say we have 2 plus 3 and their whole power is 2. So if we were to follow this, we would write 2 square plus 3 square, which is 9 plus 4, 13. But actually 2 plus 3 is, using the BODMAS rule, 2 plus 3 is 5 and 5 square is 25. So clearly these two answers are not matching and this is a wrong approach, that we distribute the whole power of a sum or a difference. That's the wrong approach here. This is applicable only for multiplication or division. Also note that there is a difference between when you say whole power, that's the rule number 4 here. Let's clarify this further. Let's say we have 5 squared to the power 3 and 5 squared to the power 3. So in speaking that's not much difference, but when you see the bracket, that clearly makes a difference. This is 5 to the power 2 to the power 3. Now 2 to the power 3 in itself is 8, so that's 5 power 8 here. And here 5 squared to the power 3, that's power of power, and they are multiplied, so this is 5 power 6, and also these are not the same. right? So these are the 8 rules that we can list so far. And remember, these powers m and n, this is a note here, that m and n could be any real number. When I say real number, they could be positive values, negative values, they could be 0, or they could be fractional as well. Fractional means, let's say we have power 2 over 3, or let's say we have power 4 over 5, or negative 4 over 5. These are fractional powers, but the rules still say the same. If we are multiplying two same bases, whatever their powers are, irrespective of they are negative, positive, or fractional, we simply add those powers. The difficulty level does rise because we are adding two fractions in this case, so that's a slightly different concept. So that's a slightly difficult part, but otherwise the rules still stay the same. Right, let's move on to our examples, and we will try to use these rules and explain them in detail. Okay, so the first set of questions is x power 4 times x power 3. This is same bases multiplied. If the same bases are multiplied, we will add their powers. So this is x power 4 plus 3, and that's x power 7. Similarly, same bases are multiplied. If no power is shown, we know that p has power 1, and so same bases multiplied, you add the powers, and that's p power 4. That's quite easy for us to understand at this stage. Again, same bases multiplied, so we write the sum of these two powers, 7 plus negative 3, and you know that this simplifies to 7 minus 3, which is finally x power 4 as the final answer. Here, division of same bases results in subtraction, so x power 5 minus x power 2, which is x power 3. Let's do the division here. So this is w power 5 divided by w power 8. If I write it like this, w power 5 over w power 8, perhaps you can make a better sense of what's going on. Normally I would prefer moving the base with smaller power, so in this case I'm going to move this w power 5 from the numerator down in the denominator. So if you bring it down, its power will be reversed in sign. Now that is another rule that we just listed, and then same bases are multiplied, so you add the powers, we get 1 over w to the power 8 minus 5, which is 1 over w to the power 3. That's one way of elaborately or explicitly using the rules. Otherwise you can simply say if w power 5 is divided by w power 8, you cancel the powers, and what powers are you left with? 3 powers in the denominator. This is d power 5 divided by d power 4, d power negative 4 here. So we move the power that is smaller. So d power 5 times d power negative 4 is now positive 4 in the numerator. Same bases multiplied, you add the powers, and you get d power 9 as your final answer. I hope it's going good. Then we have power of power rule. So if it is power of power, these two are multiplied, and we have this as final answer. Again, power of power, it's irrespective of these numbers. If it is power of power, they are simply multiplied, and we get z power positive 3. This is the whole power. Whatever this whole power of the fraction is, this whole power is distributed to the numerator and the denominator. So this 1 gets the power negative 3, and then this w squared gets the power negative 3, and this is 1 to any power will be 1. W squared to the power negative 3, that's power of power, so they will be multiplied, w to the power negative 6. But the norm is we represent our answer, or we present our answers with positive power. So if this is negative in the denominator, we will shift it to the numerator to make it a positive power. Another note that you can make here is if you have the whole power negative, you can simply invert the fraction. In other words, you reciprocate the fraction. You say w squared over 1, you have reciprocated the fraction, and you reverse the sign of the whole power. I'll repeat. If you have a negative whole power, you reciprocate the fraction inside, and you change the sign of the power, and that's w2. This whole power is distributed to the numerator and denominator, w squared to the power 3 and 1 to the power 3. Power of power, so this will be w power 6 over 1, which is again final answer w power 6. Now this is sometimes not necessary to show, but I'm explaining all this, showing you all of this just for the sake of clarity here. You may want to skip some of these steps and you can write the answer directly. That's absolutely okay. Alright, in question number 2 we have the whole power in all of these examples. So let's say what we have. This is the whole power of a product, so I know this whole power will be distributed to each of the bases. So A gets this power times B gets this power, and in our final answer we won't show this multiplication sign. So our final answer is A power 4 times B power 4, or simply a power 4, b power 4. Let's give this whole power to each of these bases. You may want to pause the video and try to do these questions by yourself first, and then see the answers with my solutions. This is x power negative 3, so in the denominator this will be positive x power 3. Similarly, y power negative 3, in the denominator it will be positive power, and so the final answer is x cubed 1 over x cubed y cubed. Again, if you have the whole power negative, you could have already directly done this way, 1 over xy to the power positive 3. As I mentioned earlier, if your whole power is negative, you reciprocate the fraction inside. The fraction here is xy over 1, so now it's 1 over xy, and you change the sign of the whole power, and then you again distribute this whole power to each of these numerator and denominator. Right, part C is 3 over, so 3 remains as it is, and this whole power 2 is given to each of these bases, so that's 3 squared and times a squared. Now we have 3 and 3 squared. This is 3 power 1 and 3 power 2. If you look at this, we have same bases divided. What you do is subtract the powers. So if you subtract the power, 3 power 1 is subtracted from both, and you're left with 1 in the numerator and 3 power 1 in the denominator times a squared. So that cancels out to be 1 over 3 a squared. I'll repeat, this is 3 power 1 and 3 power 2 in the denominator. So we cancel and we reduce powers. We cancel the powers like this, 1 power taken from each. If you take 1 from this one, you will be left with 3 power 0, and that's 1, and then 1 taken out from 2, which is 1 here, so simply 3. There are many explanations, but I'm trying to give you a variety of explanations. Though it may sound very easy to you, but still we can have a lot of explanation and clarity in these simplest questions as well. Alright, so let's move on to the next question. We have 3 to the power 4, so this whole power is given to each of the bases, 3 to the power 4 and y to the power 4. 3 to the power 4 is 3 to the power 4 means 3 is multiplied by itself 4 times, so that's 9 times 9, which is 81 y power 4. We don't show the multiplication sign in the final answer, and that's it. Right, again whole power of a product, so you give this whole power to each of these, so that's m to the power 5 and then n squared to the power 5, m to the power 5 as it is, but for n squared it's power of power, so again you multiply the two powers, 2 5s are 10, so that's n power 10. Alright, let's quickly do these questions. This is 2. We are done with numbers. 2 times 3 power 3 is 27, so 2a squared times 27. 2 times 27 is 54, and so the final answer is 54a squared. The important instruction to follow is simplify, so 54a squared. Now we have x squared times 3x cubed. The numbers are 1 and 3, so the numbers are dealt with. Then x squared times x power 3. If I have to show this, this is what's happening here. So the same bases are multiplied. I will have to add their powers, and so 2 plus 3 is 5. So final answer is 3 times x to the power 5. See here, this is 2 times 3 6, y squared times y squared. I'll just show here for the sake of it, y squared times y squared, so this is y power 4. Final answer is 6y power 4. This is 10y cubed over 2y squared. Dividing the numbers, what do we have? 10 and 2 cancel out, so we have 5 here. Y squared and y3, same bases divided, so you subtract the powers. 3 is the bigger power, so I'll subtract 2 from there in the numerator, and so my final answer is 5y. Okay, up next is the multiplication or expansion of the brackets. So multiply of the brackets is a simple instruction. Let's see how does it go. Whenever you have a number or a variable multiplied with a bracket, it means it will be multiplied by each of the terms separately. So what do we have here? 2 times x cubed plus this x cubed multiplied with x power 4. So 2x cubed remains as it is, and x cubed and x power 4 are same bases, so I'll add their powers. That's x power 7, and so this is my final answer. Similarly, we have y squared and y cubed multiplied, same bases multiplied. You have to add their powers, and then y squared times y with a negative, y squared times y, again same bases multiplied, you add their powers, so that's y cubed, and the final answer is y power 5 minus y power 3. Okay, up next is question number 5. So there are various ways of going at it. I'll share a few with you. Either you do direct cancellation, but I'm going to rigidly use the laws of indices. And first of all, I see the product of same bases, so I'll add the powers. This is 3 plus 4 over x squared, which is x power 7 over x power 2, and then you see that the two same bases are divided, so you subtract the powers. This is it. X power 5 is the final answer. But you can do simple cancellation at the later stages, and it will be absolutely fine with that. So what you do is when you see that same bases are divided, you can simply do the division part first. So I'll keep x power 3 as it is, times x power 4 and divided by x power 2, so you're left with x power 2 here. So I've used the division rule first, division of same bases, and so the final answer is x power 5 again. So there are multiple ways of going at it, and these are just a few. Similarly, I'm going to first collect all the bases, same bases in the numerator, so that's d to the power 3 minus 4 over d to the power negative 2, and so this is d to the power negative 1 and d to the power negative 2. Now here again we have the question, when we are dividing same bases, which one is to be shifted or subtracted. So we normally go with the smaller value. Among negative 1 and negative 2, the smaller value is negative 2, so I'll change its position from denominator and bring it up in the numerator. If you bring it up in the numerator, the sign of the power is reversed, and now we have the situation that two same bases are multiplied, and so we'll add their powers, and final answer is D. Before we move on to solving question number 6, let's just revisit the prime factorization. So if I have any non-prime number, I will first find its prime factors. This is 2 times 4, 8, and then 2 times 2 is 4, and then 2 times 1 is 2. So I can express 8 as 2 times 2 times 2, which is actually 2 to the power 3. Remember, the prime numbers are the ones which have exactly two factors, 1 and itself. So clearly 8 is not a prime number, because 8 can be divided by 1, 2, 4, and itself 8. So clearly more than 2. Also, that 1 is not a prime number, because by definition it should have 1 and itself. So it doesn't have exactly two divisors, it has just one factor. So 1 is not a prime number. So prime factorization of these non-primes, in this case we prime factorized 8, and we can express 8 as 2 to the power 3. So 2 power n on the left side and 2 power 3 on the right side. And this implies, this symbol stands for implies, or this means you have the same base and you have the same answer. What does it mean? It means that you are raising the same powers. Hence, this implies that the powers are same. So the key thing here is, if your unknown is in the exponent, make the bases same. So I'm going to express the same here. First of all, 81. So the prime factorization of 81 is 3 times 27, 3 times 9, and 3 times 3. So 81 is the product of 1, 2, 3, and 4 3's. That's 3 power 4. So 3 power n is equal to 1 over 3 power 4. I need to make both the bases same. So this is not the same base. It will be same if we shift it up in the numerator. So 3 power n is equal to 3 power negative 4. You remember, if we shift from the denominator to numerator or numerator to denominator, the sign of the power is reversed. And again we have the same situation. We have the unknown in the exponent. We have made the bases same, and then we'll say that this implies we were raising the same power, and that's job done. Now in our next question, it says simplify and express with positive powers. Instead of this question, let's make it our habit that whenever we present our answer, we present with the answer with positive powers or positive exponents. So 3 as it is, this negative power is with x the base, and so what I will do is I'll shift it across the fraction and bring it down to the denominator, and now its sign is positive, and this is 3 over. So the simple way of remembering it is, whenever we have to change the sign of the power, we shift across the numerator and denominator. These are the possible positions. So guys, this is our final answer for part A. Let's see part B. First of all, part B is the fraction 3 over 4 has a power negative 1. So one way of doing it, as expressed earlier, that you simply reciprocate this fraction inside, and the sign of the power will be reversed. This whole power will be reversed at once. And then u power negative 3, so in the denominator it will be u power positive 3. If you don't see the denominator here, it's actually 1, and when I shift it down, it's 1 in the numerator and u power 3 in the denominator. Power 1 of any number doesn't change any number, so we have 4 over 3 times 1 over u power 3. But this is not the way of presenting. We would not show this multiplication sign, so we have 4 over 3u to the power 3 as a final answer. Right, so going good. I hope the laws of indices are making sense. If you think that you need to revisit the formulae again, so I would suggest you write the formulae, all the laws of indices on one go, and always keep that in sight whenever you are solving these questions. Okay, so write in the root form. Now before that, let's see a very simple observation. How do you read this? You read it as the square root of this base x, and you express it as x to the power 1 over 2. Let me show. The power currently here is 1, and what you're doing is, when you're taking the square root, you're dividing this 1 by 2, and now you're taking the half of the power. Let's take another instance. Let's say if we have the square root of x power 4. So when you take the square root of this x power 4, what would you do? You will have square root, this radical form, converted into exponential form. Square root means 1/2 of power. Similarly, if we have cube root, that would be 1/3 of the power. And how would you show that? You write this radical sign, and then you write this 3 for indicating the cube root here, and this is how you write it. Cube root, it will be x to the power 1 over 3. And if we have x power 6 and cube root taken of that, what would you do? X power 6, and then you take 1/3 of this. Power of power, they are multiplied, and 6 times 1 over 3 is 2. So you're left with, so the short of this is, when you're taking the square root, you're taking 1/2 of power, you're taking the cube root, you're taking 1/3 of the power, and then if we generalize that, let's generalize. Let's say if we have any root, and we say that this is the qth root of x, then what happens is, we will write it as x power 1 over q. And to make it more elaborate, let's say we have x to any power p, and you're taking the qth root, and this is the more broad picture that we will use in our future. X to the power p, and you're taking the qth root, we would read it as qth root of x to the power p. So whenever you take the qth root, it means you're multiplying this power by 1 over q, or in other words, you're dividing this power by q. You see, if you multiply these, this is power of power, so they will be multiplied, and this can be written as p over q. So in short, what we're going to say, if it is the qth root of x power p, we will write it as x power p over q. So this is our important result here. Now we have write in the root form. Whatever this denominator is, I can write it as m power 3 times 1 over 4. Even before that, let's write it as m power 3 times 1 over 4. I'll keep this fractional power here, 1 over the unit fraction here, and so keep that, bring that, everything else inside the bracket and show it as this. And then this 1 over 4 is now converted into the 4th root, and mq is inside it. Let's do this drill again. So we have m to the power 2 over 3. I'll express it as m to the power 2 times 1 over 3. I'll make this unit fraction. The unit fraction is the one which has 1 as a numerator. And now I'll show this as m squared to the power 1 over 3. It's power of power, they will be multiplied, so we are doing the right way. And then when this is expressed, you will write 1 over 3 as the root. If it is 1 over 3, that means the cube root of this base, whatever that is. Let's try to do it here. So x power 3 to the power 1 over 5, and so this will be the 5th root of x cubed. I think it sounds easy now. This time this is -2. Beware, first of all, make it into a positive power. So this is 1 over k to the power 2 over 3, and so k squared to the power 1 over 3 in the denominator, and then 1 over 3 is now the cube root in the radical form, and beneath it is k squared, and that's the final answer. Okay, up next is evaluate. So what we're going to do is, again, we will use the prime factorization, and we will use the fact that this fractional power is the root sign. Okay, so 9 is 3 squared, because 3 times 3 is 9. Power of power, so we multiply, and when you multiply 2 and 1 over 2, they cancel out to get 3 as your final answer. Similarly, 27 is prime factorized, and we get 3 9s 27, 3 3s 9, and 3 1s 3. So 27 is expressed as 3 to the power 3, and above we have the power 2 over 3. Again, power of power, we multiply them, so 3 times 2 over 3, and we get cancellation in the power here. This 3 and this 3 cancel out, So we are left with 3 to the power 2. Either you leave your answer like this, or 3 squared is 9. That's your final answer. Now we are not using the root or radical sign rigidly here, because we are able to manage that otherwise. Okay, now question number 9, we now see the radical signs. So first we will convert from radical form in the index form. In fact, this is our task, to write it in the index form. So we have y power 5, and cube root means 1/3 of the power, and then power of power means they are multiplied. So this is 5 times 1 over 3, which is 5 over 3. Let's give it a try for here. This is y power 6, and this is the fifth root taken. So fifth root means 1 over 5 of the power, and then power of powers, the powers are multiplied, so 6 over 5. And for this one, we have the cube root of all of this. So I'll write it as a power 6 times b power 9 to the whole power. Cube root will be converted into the index form, which is 1 over 3. And now we will distribute this whole power to each of the bases, because these bases are different. So this whole power is distributed to each of them separately. So a power 6 gets this whole power, times b power 9 gets this whole power, and then we have power of power in each of these cases. So we get 6 times 1 over 3, which is a squared, and 9 times 1 over 3 is 3, so this is b power 3, and our final answer is a squared b cubed. Okay, our next question is simplify the following expressions. So basic laws of indices are still applied here. Whatever the fraction powers are, be it fractional powers or integer powers, same bases are multiplied, and now I'll add these two powers. So this is 3 over 2 plus 1 over 2. The added difficulty is that we have to add fractions, but you can see my other video on how to add fractions. This is 3 over 2 plus 1 over 2, which is like fractions, so this is 4 over 2, and hence that is 2. The final answer is u squared. Similarly, this is again same bases multiplied, so we will add the powers, 4 over 3 plus negative 1 over 3, but we will have to do this separately here. So 4 over 3 plus minus minus, these are like fractions. 4 minus 1 is 3 over 3, hence this is also 1. This is v to the power 1, and we don't show power 1. Okay, again we have to evaluate. This is r cube to the power 1 over 3. This is power of the power. If that's the case, then we multiply them. 3 times 1 over 3 is 1, and so our final answer is r. Don't show this power 1, please be careful with that. In the next question, it's the same scenario, that some value is multiplied with a bracket, and we know that they will be multiplied by each of them separately. The only difficulty level here is that the fractional powers are involved, but nevertheless we will use the indices, laws of indices as it is. That's x power 1 over 2 times x power 1 over 2. So the first product is done, and then for the second product we have x power 1 over 2 times x to the power negative 1 over 2. Same bases are multiplied, so we add the powers. That's 1 over 2 plus 1 over 2 plus, same bases are multiplied, we add the powers again, so that's 1 over 2 plus negative 1 over 2. 1 over 2 and 1 over 2, in other words half and half make it 1 complete, so that's x power 1, and we don't show the 1. And then 1 minus 1 half minus half, it's x power 0, and so the final answer is x plus x power 0 would be 1. So that's your final answer. Okay, so question 12b is again of the same sort. You are multiplying this bracket with the x power negative 3 over 4. The only added difficulty is we are involving fractions and powers, but nevertheless we first multiply x power negative 3 over 4 and x power 7 over 4. X power negative 3 over 4 times x power 7 over 4 minus x power negative 3 over 4 times x power negative 1 over 4. Now same bases are multiplied, so what do? We add the powers, 3 over 4 plus 7 over 4. Similarly in the next term we have x power, again we have same bases multiplied, so we will add the powers. Now negative 3 over 4 plus 7 over 4, the fraction solved is 4 over 4, which would be x power 1, and then here it's negative 3 over 4 and negative 1 over 4. Negative 3 over 4 and negative 1 over 4, which results in negative 1. So this is x to the power negative 1. So x minus x to the power negative 1. We might think that this is our answer, but again I already mentioned that we would prefer writing our answers with positive power. So we will now convert that into 1 over x minus 1 over x. That would be your answer. Or if you want to simplify, you can write it as x squared minus 1 over x. Do give it a try and try to get this if you want to try it. Alright, up next is, this time we have two terms in each bracket, so we will have four terms. So first term is 8 squared times a power negative 2. So a to the power 2 times a to the power negative 2. And then we have a squared times 1, which is simply a squared. And now it's the turn for 1 times a to the power negative 2, which is a to the power negative 2, and then 1 times 1 is 1 again. So here we have same bases multiplied, we add the powers, and you know what's 2 plus minus 2? That's 0, so a to the power 0 plus a squared. A to the power negative 2 should be written as 1 over a to the power 2, that is with the positive power, and that's 1 here. Any number to the power 0 is 1, so that's 1 plus a squared plus 1 over a squared plus 1. And now we add these ones here, so our final answer is a squared plus 1 over a squared plus 2. And that's the simplest form. And now in this part, we have again two brackets with two terms each, and we multiply them. So x power 1 over 2 times x power 1 over 2 plus x power 1 over 2 times 1, which is same. And then for 1 we have 1 times x to the power 1 over 2, which remains as it is, and then 1 times 1 is 1. So we have x to the power 1 over 2 times x to the power 1 over 2. We are multiplying same bases. We will add the powers 1 over 2 and 1 over 2. It's half and a half, 2 halves make 1, so that's x power 1 plus x to the power 1 over 2, x to the power 1 over 2. These are like terms, so that's 2 of them plus 1. We will write the final answer as x plus 2 times x power 1 over 2 plus 1. Let's say if you were to write this in the radical form, wherever possible, we will write the same expression as x plus 2 times root of x, square root of x plus 1. So guys, in this video we briefly discussed the rules, then we applied the rules, and we try to expand our working as much as possible. And it's not necessary to show all the steps, but one should be very clear of where and how the rules are used. And if it comes to fractional powers, it's absolutely the same rules except for adding, subtracting or multiplying fractions. As it comes for the radicals, remember the qth root means divide the power 1 by q. If it is a cube root, you divide the power by 3. If it is a square root, you divide the power by 2. Similarly, the qth root will be divide the power by q. This is the most generalized manner of remembering that qth root of x power p will be p divided by q. I have this whole discussion on a canvas, and you can access this canvas through the link that I have in the description. And instead of going through the video and play and pause, you can simply access the whole discussion here. Once you have gone through the video, try to do them by yourself, and then you cross-check with the discussion here. If you have any feedback, have any concern, you can definitely put that in the comments box. Please like, share and subscribe to my channel, and please hit the bell icon. For more videos, please let me know if you have any other video that you want me to make, and I'll definitely get back to you with that.